Okay, so hello guys, welcome to another problem solving session with Special Maths Academy. So my name is Wukume Jaife, and today we're looking at problem 2 of the Junior Mathematics Olympiad second round. And the problem says to find a necessary and sufficient condition such that find the necessary and sufficient condition such that one root of the quadratic equation ax squared plus bx plus c equals 0 is the square of the other, right? So that's our problem. Okay, so before we start going to this problem, I felt this problem was really difficult because of the fact that it's actually a two-part problem. The first part is the keyword necessary. So we have to find something first, and we have to prove whether something is sufficient to guarantee. So it's actually two parts. So doing one part, and this is actually a student can do one part and forgets to do the other. You can't do the sufficient part without the necessary part. I think that's obvious. That's why necessary comes first before sufficient. So but if you just do the necessary part, which I believe is the more difficult part, because the necessary part is where you find the condition, and not doing the sufficient part, you could also lose points. And actually doing the necessary part was not so easy. So I believe that students could have lost points here because of that. So let's look into the problem now. It's still not that difficult. It's still doable. So they said to find the necessary and sufficient condition such that one root of the equation ax squared plus bx plus c equals 0 is the square of the other. So we'll first establish the condition. So we establish the condition. So they said one root is the square of the other. So we can say okay, let's say this is the necessary part. So you can say that the roots of the equation be p and p square, right? Yeah, since one is the square of the other, so that condition is satisfied. So we know that p plus p square is minus b over a. This is sum of roots. And we know product of roots is p times p square. And we know that is equals to c over a. So we have that p plus p square is minus b over a. When you multiply this out, this is p cube. And we have that p cube is equals to c over a, right? So we have these two conditions. So far we have this now. So whatever we're going to establish is going to be independent of p and p square, whatever. So whatever we're going to, so our plan now will be to try to use these two, try establishing a relationship between ABC, right? Using these two equations. So I'm going to erase some sections now. So that's our plan. That's just what our plan. We don't know what that relationship is, but that's how we want to work, or we like to work like that. That would likely be the best direction to go through. So at this point, it's from now on, to boil down to actually what we know, because this p cube, this p plus p square, I can write it as this. So this part is just me playing around trying to see what I can get, right? So we have that, and I can write this as minus b over a. So if I bring this one here, so I have something like p squared plus p plus 1 is minus b over a plus 1, which is a minus b over a, right? So somebody might ask, why am I doing this? So my main motivation for doing this is because I'm seeing stuffs like q p squared plus p. So if you've ever seen this factorization, a cube minus 1, you know this is p minus 1 into p squared plus p plus 1. This is a common factorization. So if you look, this part is somewhere around here. This is also like p cube is also there. So I want to like use this, so I don't just have this. So I believe that for now this is still like just thought process. I'm just going through many things. This could also not work because I don't know what the condition is. I'm not trying to like use what I know to find something new. So for now, I don't even know the aim of what this is going to give us, but I believe that something useful should come out. So my reason of considering this, I'm trying to work towards this, is because I'm seeing p cube and I'm seeing p squared plus p. So the only parts I'm not seeing are this plus 1 and this minus 1 parts, and I can easily control these two sections. These parts are controllable. I can bring in the minus 1 and the plus 1, which I've done because I brought in the plus 1 here. Now we have this as a minus b over a, which is actually making sense. So I can come to this second equation now. This is p cube equals c over a. So I can subtract 1. I have that p cube minus 1 is c over a minus 1, which is implying that p cube minus 1 is c minus a all over a, right? So I have this now. I also have this. So let's write them out. So I'm going to clean again. So for now, like I said earlier, we're just investigating and playing around with what we know because establishing the condition, we haven't seen the condition before, we don't know what it is. So we're just trying to use what we know to like get some things out. And so I told you my motivation for trying to do this because that cube and p squared plus p stuffs are like familiar. So I have that. So we can now come back. We know that this p cube minus 1 is p minus 1 into p squared. And we know what this is. This is p cube minus 1. We already got it as c minus a over a. So this is like c minus a over a. We don't know what p minus 1 is, but we know what p squared plus p plus 1 is. This is a minus b over a. So obviously we know a is not 0, right? Because then we have this is like a linear equation. So that's not true. So obviously a is not equal to 0. So I can just multiply it by a. So I have that c minus a is p minus 1 times a minus b, right? I have something like p minus 1 is c minus a over a minus b, right? So then I only have that. Then I have something like p is c minus a over a minus b plus 1. I'm going to clean this out now. So then we have that this is like c minus a plus, after using LCM, which is c minus b over. So okay, fine, I know what p is now. So p is c minus b over a minus b, right? Then if you remember, we know that the initial set of equations, you had that p cube is c over a, right? Okay, then so now we have p minus, we have what, this is p, we have this, and we also have that this is true, right? So what can we do now? So let's still like investigate. So far so good. So let's try subtracting. Let's just, So if we come back to this equation now, if we come back here, or using this now, this one I just boxed. Let me use another color. If we come back here and plug in our value for p, we have that p square. So in place of p now, I'm putting this plus c minus b. So I hope everything is clear to this point. Is like minus b over a. So only p square will be minus b over a minus c minus b, right? Which is LCM is a into a minus b. Then you simplify minus b into a minus b minus a into c minus b. Expand, which has to like minus ab plus b square minus ac plus ab over a into a minus b. So minus ab plus ab cancels out. So this is like equals to b square minus ac over a into a minus b. So have that p is c minus b over a minus b. I'll have that p square is b square minus ac over a minus b. So what do we notice? We notice that the square of this, if you square this, you can call this like 1 and 2 now. So I'm going to erase again. I'm just erasing the sections we don't like need out. So the whole you can follow. So I'm just erasing first. So we know that p is now okay. We know that p is c minus b over a minus b, and we know p square is b square minus ac over a minus b. So if I square this now, square both sides, I have that p square is c minus b all squared over a minus b all squared, right? But this p square, they are the same, so it means these two are like equal. Since p square, they are like both p squares, so it means that c minus b all squared over a minus b all squared is equals to b squared minus ac over a minus b over a minus b, right? So this is p square, yeah. So I can multiply it by a minus b square, so I have something like, okay, next something is missing here, sorry, a into a minus b, yeah, it should be an a here, so this should be a into a minus b, yeah. So this is a into a minus b. So if I multiply it by a minus b square, I have something like c minus b square equals b square minus ac over a into a minus b. So all I did was multiply through by, okay, let me write that again so don't get confused. So we got that, we know this is possible, this is true. So let's clear fractions like multiply through by the LCM. So the LCM is a into a minus b square. So multiply through by the LCM. That's, so this MET means multiply each term by the LCM. So when you multiply by the LCM, you have something like A into C minus B squared is equals to B squared minus AC into A minus B. So this is the relationship between the variable conscious ABC. So this is a relationship. I think this, and this is our necessary condition. So this is the necessary condition. So we've used the fact that if one of the rules is the square of the other, we've used that information. So we've used this information to navigate down to this. So we started with this from sum of roots, the product of roots, which is p times p squared, and then we kind of use this to navigate to this through algebra by exploiting the fact that this is true. Let me write this in. So this was like we use the fact that this is true, so we had to make some manipulations. So this was how we like moved. So this is a condition, and this condition is actually sufficient. So this is the necessary condition. So this is one part of the problem. So if you do this properly, you should get like 3 points. So here comes the second part, proving that this condition is sufficient. So let's write this condition somewhere at the top so we don't forget it. So condition. Before we even try proving it, let's check if the condition is correct. Because if it's not correct and you're trying to prove something that's not correct, I'm going to spend all day. So I'm going to clean all this now. Okay, so this is our condition, right? So before we go on to prove the sufficient part, this is the condition. A into C minus B squared because B squared minus AC into A minus B, right? So let's check. So let's take an equation. Okay, let's take sample equation. Let's take an equation where the roots of the equation are like 4. One root is 4. Let's say x1 is 1 root. For then the second root, x2 is x1 square, which is 16. So know that from the sum of roots is this is x squared minus, you know this formula, sum of roots x plus product of roots equals 0, right? So the sum of roots here is 16 plus 4, which is so 20. So this is something like x squared. Product of roots is x1 times x2, which is 64. So this is a sample equation, and this equation, we know that one root is the square of the other. So we can compare with this. This is 1. So automatically we have that if we compare this, we know that A is 1, B is minus 20, and C is 64. So let's check our condition. Our condition says that if this is true, if one root is the square of the other, then this equation, this identity holds. So let's check. So let's plug A equals to 1. A equals to 1. Our C is 64. 64 minus 20 squared. Our B square is minus 20 squared, which is 400. Minus A times C, that is 1 times 64, which is 64. Into A minus B. 1 minus 20 is 21. So this is 1. 64 minus 20 is 44 squared. Okay. Is that correct? Let's see. Minus 20x. Okay. A minus B should be. I'm seeing 21 somewhere, which I don't think I should be seeing. Let's still go on. This is 400 minus 4. 6 minus 2 is 4. 44. So 44. I don't think I'm seeing something that's not there. Let's see. Where the error coming from? So this is A into C minus B square equal B square is 400 minus A times C minus 64. 400 minus 64 336. A minus B is 21. I don't know where 7 is coming from though, because I'm seeing a factor of 7 somewhere. If we break this down, this is 1 times 11 times 11 times 4 squared. And I'm not seeing the factor of 86 there. So I think there's a problem now. So I have to check that. Okay, it should be C minus B, not B minus C. Okay, it's actually C minus B. Yeah, I see where it's coming from now. I just saw that. So this is why you should check stuff. So C minus B all squared. So here should be 64. So this should be 64. Sorry, 64 minus 20, which is 84, right? I was almost worried there. So this is 84 actually. Wow. I almost had a heart attack there somehow. I was like, all those hard work for nothing. So this is 64 minus 20. There should be an extra minus sign here. C minus B, just so you don't think we're doing fraud. There's no fraud in math. This is 64 plus 20, which is 84. So this is 84 squared. And we get this is 336 times 21. So we can break 84 down as 7 times 12, which is 7 squared times 12 squared. We know 336. We can break this down as 8. Then can break this is 7, 12, 4. Okay, into 12, 1. So this is 4 times 7 times 12 times 3 times 7. 21 is 3 times 7. So this 7 pairs, 7 square. 3 and 4 pairs, 12 times this, so that's 12 square. So we have equality on both sides. So we have 1 times 7 squared times 12 squared equals 7 squared times 12 squared, which is true. So our rule holds, our condition holds, right? So far so good. Yeah, so I almost froze there. Imagine that happened to a student in the exam hall after all that hard work. So this is one reason why when you do something, before you conclude that you're actually wrong, you want to check properly, because things do happen. So our condition holds. We verify that. You can still pick other values, but it will still hold anyway. So condition holds. Yeah, so if you are able to execute this properly on the exam, you could get like 3 points out of the possible 7. So now comes the second part, because the second part is actually what I call reverse engineering. So we know that the condition holds. So we've proved the necessary parts. So this is the necessary part. Then the second part, which is what we're going to do now to get the remaining 4 points in the problem. Okay, so now here comes the sufficient part. So let me explain how this part will look like. So this part now is going to take something for you. This part is going to give you, okay, assuming you have an equation, you have ax squared plus bx plus c equals to 0. Then you also know that a into c minus b squared into a minus b is given. Right? You know these two. Can I use these two information? Are these enough to conclude that one of the roots is the square of the other. Roots of the quadratic is the square of the other. So what does this mean? So it means that it's like, now I give you this part of the problem, I give you the equation, I also give you the condition. The condition was what you found, but then I take away this part, but this part is not here now. So now you have this condition, you have the equation, you have the condition, but you want to prove that this has to hold. That means one has to be square of the other. So that's what the sufficient condition means. It's like, how will I explain this? Like, they give you 200 naira, and they give you, they said you people are 7 people. Is that condition enough to ensure that all of you can split the money evenly in whole numbers? So that's what you want, just want, like something like that to show. So does that always mean that if you have that, you can always have this square condition true? Because now they're giving you this is what the sufficient part is. So it's like reverse engineering. I give you this, I give you the condition. So in the exam, though, I give you the problem, I give you the condition, then I ask you to prove that the problem is complete, that these two conditions 1 and 2 are enough to agree to show that one of the roots has to be square of the other. That's what this sufficient condition means. So that's what we're going to prove now, that this equation in conjunction with the condition we got is enough to show that one of the roots is the square of the other. So this is where the sufficient part comes in, and this part will have more marks than the necessary condition part. So this could be a 3 marks, and this could be 4, because showing this second part is a little bit much more tricky. So let's go into that. So let's try proving the sufficient part now. So to start, you can say, okay, let the roots of ax square plus bx plus c equals to 0 be m and n. So what you want to do now is you want to show that either aim, so this is your aim, to show so this is a 2-part problem. So your aim now is to show that either m equals to n square or n equals to m square. This is what you want to do now. I want to show one of this is true. So how do you go about that? Okay, so you know that sum of roots m plus n is minus b over a, right? The mn is c over a, right? Then you also know that you have this condition. We also know that we have this condition. So then I want to use this 1 and 2 to show this, to show 3. Use 1 and 2 to show 3. Wow, so this is something to work about. So let's just see how can we actually go about this. Let's just try what we know. So my first guess would be to try writing this, try expressing the condition in terms of m and n. So the first thing we have here is c minus b. So you can call this you know that, let's say m plus n is minus b over a. Let's call this 4. We know mn is c over a. Let's call this 5. Then if I add 4 and 5, I'll have that m plus n plus mn is c over a minus b over a, right? When I sum, which is C minus B over A. So that means C minus B is A into N plus N plus Mn. So I keep this way. So let's like put this in a separate box. Let's use blue. Let me write this one. Right? So we've gotten this condition. Then the next case now is writing B square minus AC in terms of whatever that is. Okay, so I'm going to clean this now. So from 4, we can make this. This implies that we know that if I multiply both sides by A, I have A as N plus N equals to minus B. Then I square both sides, I have A square into N plus N squared equals B square, right? So I have B square. Now therefore AC, we have Mn equals C over A. So this means that AMN equals C. I'm multiply both sides by A, and then this means that A square MN equals AC, right? So I can call this equation 6 and 7. Then I can just subtract 6 from 7. Equation 7 from 6 rather. So I have something like A square into N plus N squared equals B squared. Okay. When I subtract, this becomes true. Minus A square MN equals B square minus AC, right? And A square, when I subtract, can come out. I have N plus N squared minus Mn equals B square minus AC, right? And I can rewrite this as, so I put it here. This, if I expand, this is A square into M square plus 2Mn plus N square minus Mn A square into M square plus, so when I simplify, so I have this. So I know what B square minus AC is now. So it just remains A minus B. So we've expressed this. Remains A minus B, right? So let's clean again. So we don't go too far from the expression. The expression in view that we're trying to like use M and N to rewrite. So remaining A minus B. So how do we go about that now? That should be a question I want to think about. Okay, so A minus B is the next thing. Hmm. A minus B. Okay, so we could write this as m plus n, right? Then I add a to both sides. From this, multiply both sides by a to have a. So then I add a to both sides, will be minus b plus a, which is a minus b. So we have this is a out into m plus n plus 1 is a minus b, right? So we plug it here. So if we're putting everything we have, I think there should be a square here, right? Yeah, there is. Let's check. Let's just check. We know that we got to get c minus b, we added both. Is c minus b. Okay. Okay, there should be no square, sorry, yeah. And we know that a into, yeah, so there should be no square there, yeah. So there is no square here. Sorry about that. It's just to be sure, because this problem was really tricky. So we know what this are now. So we just come in and plug all this. So we now use this to come here. So in place of a, I leave a there. In place of c minus b, I put this. All squared, c minus b squared. In place of b squared minus ac, I put a into, so in place of a minus b, okay, this is square outside. In place of a minus b, I put a into, so I can rewrite this as, this square means this is a times a squared. This a squared is coming from the inside. This a matches with this a square. So this is a squared times a again. So you can see a cube on both sides. So this goes out because a is not 0. It's very important, otherwise the equation is no longer is quadratic. So we have this into, wow. So let's expand now. Expand and simplify. So if you expand this side, expand, this is m square plus n square. You can just expand this by yourself, plus mn square plus 2 into mn plus m square n plus n square m. Yeah, if you expand this, you should get all this. Then you can expand this side. So this is m into everything. This is m cube plus mn squared plus mn squared plus nn squared plus mn squared plus n cube, then plus 1 multiplying everything. This is n plus n. Okay, this is plus 1 multiplying this is m squared plus n squared plus mn, right? So is there anything we can, like, similar terms we can add up? Yeah, they are. So mn square is 2. Let's just like simplify. So I felt this problem was like a really difficult one for a junior. Maybe it was just there so the exam won't feel so trivial after all. So you pair all the cubes comes together, m cube plus n cube. So to stop students from getting everything, I thought that was why it was there. This is mn square. Okay, let's see. Okay, it should be m square n rather. This is m square n. So m square n plus nm square, these two, they like go together. So this is plus 2m square n. They are the same. Then mn square here plus mn square here, 2mn squared plus m square plus n square plus mn, right? So if you observe, if you remove brackets, m square takes out m square on this side, n square takes out n square on this side. They like just subtract each other out. Then we have mn all square plus 2mn plus 2m square n plus, when you expand this, expanding this now, plus 2n square m is m cube plus n cube plus 2m square n plus 2mn square plus mn, right? You see, 2m square n, 2m square n, 2n square m, 2n square m, remaining mn squared plus 2mn equals m cube plus n cube plus mn. This can come this way, so this is you bring everything this way, then you have m cube plus n cube minus mn. Mn, this is mn minus 2mn minus mn all square equals 0, right? Okay, so we have this now. Remember, this is our aim. Either this is true. So let's just do something risky. We have this. So this is our aim. This is the aim. This is what we have, right? So this is where a little experience comes in now. If I rewrite it, this is n minus n square equals to 0, right? This is n minus m square equals to 0. These two are like equivalent forms, right? If I multiply these two, so I have that. Because when you see this initially, factorizing this is a little bit strange, it's off. How do you factorize this? It should be coming to your head. What the hell is this? Okay, let's see. Can we factorize this? It looks off. So let's just try multiplying this and see what comes out first. So n minus n square times n minus m square equals to 0 too, right? If I expand this, I'll have mn minus n cube minus m cube plus m square n square, which is mn all square, equals to 0. I multiply this by 0, I have m cube plus n cube minus mn minus mn all squared equals to 0. Can you see? So this, so when you expand this, you will get this. So you can factorize this to be like this. So let's try factorizing this to look like that now. Let's try factorizing. Let's see how that will look like. This is n plus n. So let's see this place. Let's just like try factorizing now, because now we know what the expansion will look like. So when you expand that, you get that. So let's see if we can factorize. Now we can factorize. Am I saying let's see? We can, because we already confirmed that by the expansion. So let's try pairing terms. So m cube minus mn plus n cube minus m square n square equals 0, right? If I bring out m, I have m square minus n. If I bring out n square, I have n minus m square, right? So this m square minus n I can bring a minus 1 here. So this becomes minus 1 into minus 1. This is minus n squared into m squared minus n. When I bring out minus 1, the order has to change. So this is m squared minus another m minus m squared. These two are the same thing. So this is m. So I'm sorry about that. So this is m squared minus n into m minus n squared. Yeah, equals to 0. So it's either m squared minus n is equals to 0 or n minus n squared is equals to 0. So that means m squared is either equals to n or m is equals to n squared, right? So we've gotten what, so this was our aim. So aim completes. So we've moved that. So we've shown that if you have this, so we've shown that if you have this and this, then the roots are squares. Then one root is the square of the other. That's what we have shown now. So we've shown the sufficient part. So if you can do this as well, you get the remaining 4 parts. And so this is the end of the problem. So what even made me think of trying to factorize this? So the last step was factorize the blue parts. Factorize. So one of the main reasons why I decided to factorize, because when I expanded this aim, so this is why I call working backwards. I work backwards a lot. So when I expanded the aim, when I expanded this, I came back to this. So this is what made me decide to, okay, try factorizing. So factorize it and you get all this out. So if you do this, you get the whole 7 points. So for this problem, I felt this problem was the icebreaker for the junior competition. Getting the condition was one thing, then showing that it works was another thing. So if you as a junior student can do this, then you deserve a perfect score. I felt this problem was just there to make sure people don't get everything, because I felt the problems were really trivial. But once again, there's always an icebreaker there to stop people. So we've come to the end of this problem. So you can rewatch this video if you don't follow all the steps. Because I know that this might be a lot to take in. It's actually a tricky problem. So we've come to the end of this problem solving session. Goodbye for now. I'm still Obukome Ejaife, and we'll see you in another problem solving session.